In the previous units, we discussed about axial loadings, then we discussed about different states of stresses, the transformations, majorly in the plane stress condition, and then we came into torsion. Okay, and then if you remember, at the beginning we had said that we will be talking about three major kinds of loading configuration. One is axial loading, one is torsion, the other one is bending, and this unit 4 is towards this bending, and especially like the other two, in this case the bending will be pure. Okay, so in a way we can say that this is pure bending. Now what exactly is pure bend? But before that, I'll just see if I can show this. So now if I try to bend it like this, so you are seeing that, right? So this is the action of bending, and if you observe it properly, I am using just a minute. See, I am using two fingers at both the ends, and I am applying in a way a moment at both the ends, because I am with a single finger I cannot apply that. Okay, with single finger I can apply a force which will result in some moments. We will discuss about that in a way, but it is, if you see, the bending is not so prominent, but if I twist it like this, the bending is quite prominent, right? And then you know that when I am applying two equal and opposite forces, I am actually producing in a way the moment, and that action. So in contrast to twisting, so twisting, maybe if I can show this, whether I don't know whether it will be visible or not. So twisting is applying the torque in this way. That means I want to, this is highly stiff in this against torsion. Okay, but you understand. So if I pull this, it is axial loading. If I twist it, it will become twisted, and if I am bending, it will be bent. So these are the three conditions, and the canonical configuration, if we want to draw, we will draw it like this always, that see, this is a moment and this is a moment. In fact, when I was bending it, I was bending it downwards as opposed to the picture which I have shown, and that will be in a way this way. Now why I am saying this is conventionally this is considered to be positive, okay, and this bending downwards is called negative. So if I apply the same moment at both the ends, so this one is called a positive bending. Okay, the curvature upwards. And I as usual I always draw the other two conditions so that you can correlate with. So this was for axial loading maybe, and this is for it's bad drawing. For say torsion. Then to summarize, here it will be force, here it will be torque, and there it is the moment. So these are the three canonical representation of three pure. So this is sort of pure axial loading. This is pure torsion and this is pure bending. And now this unit is about this because we have already finished these two in unit 1 and unit 3. Okay. Now, and then if this is the pure bending case, we should also have an idea about what is impure bending. Okay. Just as an example, because most of the time students have this confusion about this case. Let me draw that case. Suppose I have a beam like that, okay, and I have attached this to, I'll fix it properly, say like this, to a wall which is rigid. Okay, and now if I am applying not a moment but a force like this, generally intuitively this also will bend the beam, obviously, but is it a pure bending? It is not, because if you see this, what's happening is if you consider any cross section and if you pick this, the free body diagram of this portion, maybe, okay, this portion, then to balance this force which is acting, here you will also have the same force. It must be acting, otherwise there is nothing to balance this in this y direction. Okay, and because this force is creating a moment, so here you will also see a moment which you can see that this portion is applying in what direction it will apply. So it's try to bend this, so it will try to do that. So I'll draw like this. So a bending moment which is say f times, suppose this distance is x, fx, suppose this distance is x. Now this moment is required because the f times x, this force when it is generated to balance this sliding of this portion, okay, due to the force which is applied, you have to apply this equivalent opposite force, and as soon as this force comes into picture, it creates a a couple moment of magnitude f times x, but then that will be in what direction? So that will be in this direction, right? This is f times x, the couple moment. But then if there is no other moment to balance this, this part will start rotating, it will not be in equilibrium. To maintain that balance, this side of the beam has to apply an equivalent opposite moment to keep this thing in balance, and that again will be in this way, so that fx is that moment. So that means any section, so you pick, there is a force F and a moment of magnitude Fx. So now from pure bending case you can see two violations. First is there is an additional force which never we had here, except the moment m, no other external loading is there on that beam, the prismatic beam they call it, right? Means prismatic, why it is prismatic? That means it from a prism. How do you define a prism? You take a cross section and extrude it, okay? Means move it perpendicular to the area by some distance and you will get a prism. So that's how you get a triangular prism, a rectangular prism, anything. Okay, any cross section you take and extrude it. So that is called a prismatic bar, and on that you are putting this moment, and the point was no other force or no other loading in that sense was there. But here, and then one more thing, any section you pick, the moment is m, nothing else. It is constant throughout all the cross sections, anywhere you pick, if you see the equilibrium of that. Right. So just let me even draw that. So if I pick a cross section like this, and if I draw the free body diagram of this portion, maybe like that, and then this side it's m. So to balance this, you have to have the same moment m from this side. Okay, and this distance x from this end could be anywhere, and that means on all these cross sections the same moment m is acting. So that's the condition of pure bending. Now you compare that with this. Here two things are getting violated to make it impure in a way. So I'll call this, impure bending. Though many students have this confusion that this also bends, so it may be a pure bending. So yeah, so then this force at every section. So this is one of the violation, and the other one is this one. The moment is changing from point to point. The farther we move from this end, the moment's value is changing. Okay, proportion to its distance from that end. And these are the two violations why it's an impure bending. So how do we create otherwise pure bending? And first, to study the pure cases are very important, so that later on we can go and combine all these kinds of loadings in a practical situation, and then we can see that what actually is happening, because all these configurations are linear also. That means you can use the principle of superposition to talk about how things will deform under the presence of the combination of any of these things. So that's why we are studying these pure cases first. Okay, and yeah, so I was talking about if even in such a simple situation the bending becomes impure, then what is the condition under which it's a pure bending? So that is something like this, and then this condition happens at many practical configuration. So that means if you have say a force here, I will use a different color maybe. So you have a force here, a force here. Okay, means I am not talking about that moment, those two equal and opposite moment, how it can be generated even though the direct moment is not being applied, because direct moment application you will see very rarely, and that will always be generated by some forces only. And then if you have somewhere like this symmetrically placed supports in a way, then so this is F and this is F, and when I bent the ruler, in fact you saw that I applied like this. So these two fingers, the index fingers, where I am putting them, okay, so these are the forces, index finger forces, and my thumb is applying the other reaction forces, F. Okay, so and I am placing them symmetrically with respect to the center, so that a beautiful thing happens. Let's see why we call that a pure bending and where it will exist. So that's very important to understand. So if now you look at a section here, So draw the free body diagram of this. So it will be something like a small portion maybe, and you have force F here. Okay. Then here, as we had drawn in this portion, you will have both these forces, right? Both the forces will exist. This is a reaction force, and to counter this couple moment which is getting generated, you will have to apply a moment at a distance x, which will be equal to F times x. So that means in this zone the bending is not pure, obviously. Both the conditions are violated. Neither the moment is constant, and one more force is also there. So it's not pure bending in this zone. So if I draw this, impure. Similarly, this side, because it's symmetric with respect to the center, so this side also is impure. Now let's come and then see here what's happening. Suppose I take a cross section here. Let's draw the free body diagram up to this point. So this is like this, okay, and now you have a force here and another force at some distance here. Say this distance is delta from both ends. Okay. Now what will be the reaction forces? Let's see, this also I should have written F, right, because the reactions are same. Now let's see what will be the force, the reaction force here, because these two forces have already cancelled out each other. So this is 0. Sorry, this is bad 0. So F prime, if it is the reaction force, it is 0. And then what's the moment? Let's calculate the moment. Say this is the moment which will have to, because still this couple is there. Okay, the forces have cancelled out each other, but the couple moment still exists, and that will. So here, how much you will get? Suppose this distance is x. Okay, so that means this m, I'll write it here, is equal to, so this in this direction I am writing positive, so F times x minus delta, so F times x minus delta in counterclockwise direction, that is the m, and clockwise direction it's F times x, right? So minus F times x, right? So how much is that? It's F times x cancels out, so F times delta, obviously, because it just resists the couple moment which exists. So I can either you can think of like that, that is the couple moment which is of magnitude F delta, or you can think of in this way, which is a more elaborate way of thinking the same thing, and then this is true for any x that you pick in this zone. Okay, suppose this is L, so anywhere in this zone L, so this is the location where you have pure bending. Okay, so that means when I bend this ruler, okay, like this, so in this portion here and this portion here, these two zones, it was impure bending, but it was pure bending in the middle portion where the conditions of pure bending exist. Okay, so having discussed about the distinction between pure, first we defined what bending is, the canonical structure we desired, and then we discussed about what a pure bending is and what an impure bending is. And then we will in the next segment we will start discussing about some assumptions, like we did some assumptions for axial loading, for torsional loading, about cross sections, about the loading pattern, everything. So the similar thing we will do for bending, and then we will proceed further. See you next segment.